Hello, the title of my work is Study of a 7 degree of freedom wearable low-cost IMU system prototype to measure upper limb movements. This study presents a novel and practical solution for physiotherapy by introducing a low-complexity prototype system that utilizes electronics and robotics to monitor and analyze upper limb movements accurately. The system is designed to be applied in real-time physiotherapy sessions, aiding patients with mobility problems in their telerehabilitation process. The prototype system is crucial when capturing and processing the upper limb movement data. Moreover, it can be capable of performing precise and instant readings of upper limb movements during physiotherapy sessions. The real-time data acquisition allows therapists to monitor patients remotely and provide feedback which is invaluable for optimizing telerehabilitation. In this work, the accelerometer senses the acceleration caused by external forces and the Earth's gravity acting on the body segment studied. The function of the gyroscope is to measure the rotation rate of the sensor around its XYZ axis. Finally, the magnetometer role is to give information about the heading, employing the orientation of the sensor relative to Earth's magnetic field. Another crucial point is that considering pandemics like the COVID-19 one, developing an upper limb movement measuring system that can be used in future works by the patient in his house without complications is fundamental when health professionals are using telemedicine and providing remote medical assistance. It was selected to be employed the M5 Stick C Plus development kit and an HNC 5H83L digital compass intended to acquire data. In addition to an ESP32 development board connected to the computer to receive information via Wi-Fi of the modules attached to the body. M5 Stick C Plus was chosen because it's extremely compact and has a built-in lithium polymer battery. One of the modules is located in the chest, another in the upper arm, and the last in the forearm to acquire orientation of these body parts, applying them in rehabilitation practice. Arduino IDE, a simple open source software, is suggested to have the codes developed, and its serial monitor can be used to keep up with the real-time acquired results. An important differential of this project and its main objective is to explain the development of a wearable, low-cost system using inertial measurement units alongside microcontrollers in detail. It is important to highlight that this work's target public is users with at least medium knowledge of embedded electronics and robotics. Then, after the initial setup and calibration, a healthcare professional can read the patient's movements from a simplified interface. Another important advantage of this work, taking into account others in this field, is that through serial monitor of Arduino IDE, the movement names performed by a person alongside the angles reached when executing single or many actions can be visualized in a simple way by the healthcare professional. Naming and showing the movements on the serial monitor is possible since each movement has a determined range of motion. In order to fully reproduce this project, it is needful to follow the steps shown in the flowchart of the figure shown. First, developing an upper limb model employing the Danavich-Rothenberg convention to write the chest, shoulder, elbow kinematic chain is necessary. The second step consists of calibrating the sensors that will be used in the project, which will give orientation information about the movements performed. Then, it is needful to obtain orientation estimation applying a data fusion algorithm for this purpose. At last, it is time to do forward kinematics to know the positions and orientations of the upper limb segments. In this work, it is presented a model for chest, shoulder, and elbow movements with 7 degrees of freedom. The bony structure of the spine enables the movements of the trunk or torso. Moreover, this axial pile of bones can move conjointly over a much greater range of motion and individually within a short range of motion. The movements that the spine can perform are rotation, flexion, extension, and lateral flexion. Considering the shoulder joint, it is represented as a ball and socket joint with 3 degrees of freedom of rotation: the abduction, adduction, the flexion, extension, and the internal external rotation. Taking into account the elbow, it is able to act as a ring joint that permits performing the forearm pronation supination. The Navitt-Rothenberg convention is employed with the aim of writing the kinematic chain. For each pair of linked frames I-1 and I, which are 2 consecutive coordinate frames, there are 4 Navitt-Rothenberg parameters that represent the geometric correlation between them. The Navitt-Rothenberg parameters are shown in the table. The parameters A, alpha, G, and phi represent the link length, link twist, link offset, and joint angle respectively. LC and LUA express the length from the chest to the shoulder joint and the length of the upper arm, respectively. These segments are measured for each patient. If these segments cannot be measured, the patient's height can be used to compute an approximation. A gyroscope measures the angular speed in each of its 3 axes. As a result, the output value has to be 0 if the sensor is stable or moving ahead on any axis without rotation. To calibrate this sensor, the offset value is subtracted from each axis. The output values of an uncalibrated gyroscope will not be 0 even if the sensor is without any movement. These uncalibrated outputs are used as offset. Thousands of samples are usually averaged to acquire the gyroscope's offset. The sensor is calibrated using these equations below. An accelerometer measures the total acceleration in each of its 3 axes. To calibrate this sensor, the user can place the uncalibrated sensor on a flat surface and register the acceleration value is measured. An accelerometer in ideal conditions should measure -1g pointing to the z-axis while stable and 0g if the device is in free fall. However, this situation will not always be true since some errors will occur due to pressure, humidity, and mechanical singularities. To calibrate this sensor, the user can place the uncalibrated sensor on a flat surface and register the acceleration values measured. The offset values of the accelerometer are calculated as shown in the first equation. Now, it is necessary to calculate the scale factor of the accelerometer as shown in the second equation. At last, it is time to calculate the accelerometer values in each axis after calibration employing the third equation. A magnetometer measures the magnetic field in each of its 3 axes. To measure the Earth's magnetic field, the orientation in the yaw plane is determined accordingly. Magnetometers are devices that are heavily influenced by external magnetic fields, and the presence of some metal or magnets close to the sensor lead to errors in the magnetic field measurements, rendering them unreliable. 2 types of effects influence magnetometer measurements: soft iron and hard iron effects. Therefore, it is needful to correct them to have the sensor calibrated. It is straightforward to recognize the influence of soft iron effects by plotting the magnetic output of the sensor. An ideal magnetometer should have a plot similar to a sphere, but soft iron effects distort the output into an ellipsoid. Hard iron effects are caused by materials that have constant magnetic fields. This type of effect shifts the sphere center aside from the orange. Thus, an uncalibrated magnetometer will measure the real magnetic field with an added constant offset. To correct hard iron effects, first, the offset in its three-axis is discovered, then the measured offset subtracted from the real value. Since different locations and orientations have different values of soft and hard iron effects, the magnetometer's calibration is only valid for the specific location and orientation in which it was calibrated. The figure below presents HMC5HH3L magnetometer data with hard and soft iron effects corrected. The blue graph represents data before correction and the pink graph denotes data after correction. The magnetometer can be calibrated using computer software. A pair of sensors MPU6H86, which is inside of M560C+, and HMC5HH2L are attached to the upper arm, forearm, and chest. An ESP32 is connected to the computer to receive information via Wi-Fi of the modules attached to the body. All the sensors' placement in the subject and the connections that have to be done are shown in the figure. IMUs can have their measurements hindered by drifts. To reduce sensor drift and process data acquired, the Magic orientation filter is used for MPU6H86 IMUs that are used in this project. The Magic data fusion algorithm is a gradient descent filter which is open source algorithm. The estimation of the yaw value of upper arm, forearm, and chest movements is obtained from HMC5HH3L, which is a three-axis magnetometer. First, it is necessary to apply for tilt compensation, as shown in the first two equations below. After performing tilt compensation, finally, the last equation has to be used to discover the correct yaw value. Forward kinematics is employed to find the orientation and position of each frame using the origin frame as reference. A transformation matrix is used to describe the transition between two sequential coordinate frames of index I-1 and I, which is shown in the equation below. The results of each transformation matrix can be obtained in the MATLAB software code written by the authors. After executing all the procedures to acquire angles movements correctly, the last steps are perform the initial setup, calibrate the system on the patient's body, and carry out the movements described before. It is intended to fully reproduce the system described in this work to completely validate the whole process, including the support of a medical staff analyzing the results for the sake of they are decisive in the whole rehabilitation process. It is desired to use as few as possible types of equipment in order to measure arms movements too, and at last the system will be implemented remotely so that the patient can participate in the rehabilitation of his arm movement with the guidance of a healthcare professional. Thank you.